We're yeah. uh uh-huh. Okay. All right, we're streaming the right monitor. So there is a question as to like how we're gonna get the HDMI streams up, but this should be a good start. Uh, it's possible that we'll just like blast it through the camera. I don't know. I don't know, but we'll see. All right. Lights. And it's kind of pretty deep. I think we might just do that. We might just like focus on what's let that be presentation is you standing in front. Yeah, well, like if you go and stand in front of the screen. Under those specific circumstances, it'll be okay. Yeah, and maybe a little more lighting would help. Yeah, that's. Oh, just a finicky day. Maybe. The lights here don't correlate. Okay. These are some. That's a global setting. E. Okay. Sure. Zone. You know, whatever. This is fine. This is fine. Okay. Oh man. And now it's just a matter of sharing. Ah, I'm sorry. Of a busy day, but hey, it's 2:15. This is technically the start time. Normally we get started kind of late, so that's just and then about that. Ooh, and things are a little out of focus. Good. The PowerPoint there. Who wants to present first? There's a small list of presenters. Marissa gives me the thumbs up. That'd be pretty cool. Honestly, yeah, let's do everyone that okay. Who has presentations that are strictly on HDMI? Okay, Marissa, is there anyone else that's like strictly on their laptop? Okay, all right, cool. Yeah, come over here. So let's figure out the H stuff. Okay, okay. So what is today? Right, today is like a series of oh, and I just realized I started recording. The live stream is. Yeah, we probably should share the link. Yeah, I hoping someone else might, but okay. Let me. How do we? Sorry. Oh, William said hello. Hey, William's on. William, how clearly can you hear me? Is the audio good? I've been finicking around for quite some time now. Volume is a bit low. Okay, all right. How about now? Things are a little bit better now, perhaps? Maybe? I have it undergained to avoid crunchiness, but there's only so much that can do. That's what we're trying to figure out. So hopefully we'll get that figured out. William, if you can share the link, that would be awesome. How's the audio now? Is it crunchy? Is it good? I see we're hitting the yellow zone under normal speaking circumstances. So how is that? We'll get a response in a few seconds. In the meantime, and that I heard that, so that must have popped. Okay, HDMI cables. We can pull up. It would. We'll just on there. It looks like. That's the HDMI. Yes. Much better. Okay. Wow. Good stuff. Hey. And here we are. Wow. All right. Cool. It's plugged in. Okay. Okay. All right. This is new territory here. Let's do home, please. Can we do laptop HDMI on?
That's correct.
That's correct, but that's not the right one. Let's do this one. Okay. Okay, that is looking pretty correct. Can zoom in the camera on it a little bit. Try to bring it into focus. Maybe have your head like barely visible. Okay. This is how we're gonna do things today because we just don't have the capacity to, you know, HDMI things. So as long as the audio is good, William, like if the audio is it crunchy at all? Is it like high quality? Are we good on that? It's good? Okay, that's good. That's good. If the audio is usable, that's really exciting. And that's true. Yeah, we'll see how Marissa sounds. Here you go, Marissa.
Oh.
Yeah.
Cool.
Like, I don't know. Okay. Oh wait. Yeah, here we go. Things are underway. William, if you can share the link, that would be incredible.
Yeah, I guess I can start. That's fine. Yeah, I can talk a little bit. Alrighty, I'm speaking, and you can tell me how I sound. I probably sound.
You cannot hear me.
That's fine. I was gonna say.
Questions.
Yeah, that's fine.
Yeah.
Shall I just get started? Just yeah. So hi. Cool. Okay, cool. Yeah, so I mean, Michael reached out to a couple of people who made things during the game jam to talk about what they made, and so I participated in the game jam. If you played the games, or rather, if you're familiar with the game Whambulance, that was the game I made, and if you did play it, I'm deeply sorry. And if you did not, that's good. However, the game is about you're an ambulance and you drive around and you hit people. Don't worry about that part. The most important part is that the part that I worked on was that you can pick up those people from the ambulance. But it would have been too easy, if I'm being honest, that you just, bring the car up to the person and just absorb them in, or they just disappear. I felt really obliged that it was going to be kind of wacky, and I said, why don't we just make like a robotic arm that just like comes out of the ambulance and picks them up and brings them in. So that's what I did. But that required knowledge that I didn't know yet, so I had to teach myself during the game jam, and it was actually kind of great. And I'm just going to very quickly walk through what I did. I'm really not that familiar with skeletons and bones and rigs that much, so this was a great kind of introduction to I already knew the basics. This was a step further into what you could do with them. Some of you might be familiar with inverse kinematics. I didn't know anything about inverse kinematics before this, and it seemed kind of daunting, but turns out it's extremely easy because Unity and Blender and different software now just kind of makes it really easy to work with. So the first step I did was make an arm because that's what you needed, and in Blender it's pretty simple. I just kind of made like rudimentary shapes of like a sphere and just like a prism, just to make it look like it has joints. And then I brought it into Unity. And inside of Unity, you'll see here, so we have an ambulance. That's how the game plays if you've played it. That's, like I said, I'm sorry. But you drive around, and I don't know if the audio is going to play, but I'm just going to go ahead and not have the audio because it'll be kind of overwhelming. But I'll just demonstrate essentially how the game works. I hope the audio doesn't play. Okay, good. I've been really loud. So you obviously drive around in an ambulance and you can hit people like so. and here, I'll actually demonstrate here. So yeah, I'll bring this over here. What you can do is press E to pick up the patient. Now, I'm going to just demonstrate what it does, and it's going to be kind of an overview, and I'll walk through the very few steps of what happens, but I'm going to press E. Oops, I'm going to press E here, and it picks them up. That's it. That's what it does. And like I did my best to make it kind of seem seamless and nice, but it's actually pretty simple, and that's what's really cool about this arm. So yeah, I ported it in, and all it had from Blender, by the way, was just 3 bones. 4 bones technically, because there's a 4th one right at the tip here. I ported it into Unity, and you can't see it in the game, but the arm is actually just underneath. It's just hanging out down there. When you press E, there's an animation that plays from the ambulance itself, and it's a pretty simple one. It only has the doors of the ambulance and the rotation of the doors, and then the position of the robotic arm. So I'm just gonna kind of walk through here. You'll just see the arm comes out, and then it doesn't do anything for a while, and then it goes back in. That's all that is. And during this crucial step right here is where there's a function I call right here called acquire NPC, and that's where the magic happens that I'm going to just show you. So the robotic arm is here. All it has, I'm actually going to drag it out here so you can actually see it. Oh wait, I'm playing. Whoops. Let's go here. I'm just going to drag it out so you can see. It's the same thing that I ported in. It has bones, and as you might be familiar with Michael's last presentation that he explained about inverse kinematics, when you have bones, the system knows that what bone is connected to the other. So, you know, this bone is connected, or rather, this one's connected to this one, connected to this one, kind of like our normal arm, and they work like parented objects, kind of like how you can see here. They will move with the base one, kind of like if I have my arm like this and I move this bone, everything else moves with it, everything else moves with that one, just like that. Same thing here. They're just parented, rather, I guess, children of one another. However, in order to get a skeleton to actually do things that you want it to do, you just need to give it a rig. That's a really simple step. You just have to include the animation rigging plugin into Unity. And with an object that has an armature, which in this case is just this RoboArm object, you just click Rig Setup. And what that does is generate this object. I don't touch this object. It's just there to demonstrate that, okay, now it's rigged and you can now do things with it. The more important object is I just create a game object here called tip. All it was just an empty game object, and I gave it 2 things. I gave it a little box collider, which I'll go over later. But the most important thing is this chain IK constraint. And that means chain inverse kinematics constraint. First, I was kind of intimidated by that name. I'm like, what does that mean? A lot simpler than it actually is. Constraint refers to how you can manipulate the rig and literally give the arm constraints. Just like how with my arm right here, you don't really want the elbow going, you know, all the way down because that would be bad. So you just give it a rotation constraint. You say, like, let's say if this is, you know, 0, you can maybe go from 0 to 180, but don't go further because that's no good. I didn't really go too far into the constraints of this robotic arm because I made it easy. They're just like, it can kind of just do whatever it wants. Like, it doesn't really work like a human skeleton. So that was easy on my end. But you can absolutely dive further into adding constraints to it. It's just like literally just a rotation locks. But in this case, all the chain IK, inverse kinematic constraint, says is that, okay, this is just a game object that has this element to it. Weight, I'll talk about in 1 second, but it wants to know, okay, so you're dealing with a chain of bones right now. Where's the end and where's the beginning and where's the end? And that's just the root and the tip. So in this case, the bone you see is just the first bone in this, which is this bone, and the arm. And then the tip is the very last one, which is all the way at the end here. So now it knows, okay, cool, I'm dealing with this arm up until this point. Now, all it does is say, okay, now it has this target. It's just a 3D, or just a transform. It just wants to know, okay, so what I'm going to do is I'm going to move this bone end. I'm going to move the tip to that target. That's all it wants. It just wants to know where that location is. So I'll show you here how that works. So I just have an object in the scene called target. And I'll explain how it ends up dealing with the NPCs in a minute, but I'm going to move it over here for a second, just so it's nearby the arm. That weight I mentioned earlier, this weight refers to how obedient the arm is to the pose you want to put it in. So when the weight is at 0, it's just going to stay like, think of like, you know, an A posing, like, you know, character. That's just, they're not moving. They're not doing anything. They're not complying to whatever you maybe want to tell it to do. But when you change that weight to 1, that means it fully goes into the position that you want it to go. So I'll show what I mean. If I move, I'm going to take the target here, which right now is just this object that the tip knows is where it wants it to go. So right now, you might have seen it was like right here or something. Right right now the weight is 0, it's sticking, but I'm going to move that weight to 1, and boom. It adjusts the arm in any way to go, have that tip go there, making the base not move. So I'll show that again. It just goes there. And now, because I make the weight 1, I'm going to move that target dynamically now, and you'll see the arm is going to follow it. That's all it is. It just uses that chain inverse kinematic constraint, and it just follows it around. And that could be anywhere. Just go, woo. So as you can see, with that kind of like information, or rather that, what you, yeah, actually, you have a question?
About like target arm. So what?
Right. So in that particular instance, I did consider that in mind. The question was, what happens if, like, let's say the person in this particular example is like slightly out of the way. As you notice, when I made the demonstration, there was actually a pop-up that came up and said, press E to pick up the person. I kind of just eyeballed the radius of the arm, and then I just made a box collider around the ambulance that pretty much said, if there's an NPC in that, allow the arm to go. Because if I didn't have that there, nothing actually happens. It will just go as far as it can. So I'll show you right now. If you move the target as far away from the robot arm as possible, that's it. It just tries, really wants to go that way, but it can't. But it will at least point towards it. And then, of course, if you bring it close, all of a sudden it'll snap to it. And then it'll do whatever it can to kind of just go there. And it will adjust the bones that way. Now, for example, if this was a human arm, you know, that'd be pretty bad. Like, arms don't really go 360. But like I said, that's when you would have the opportunity to actually add constraints to the bones. I didn't do that for this because I wanted it to go anywhere. So what happens is, in that animation that you saw earlier, in the ambulance, this acquire NPC function is simply, it's in the code here. All it is this, and what it does is, right when it gets called, the animation happens, and then the function the function is called, and then, yeah, like I said, I just add this empty space if there's no actual transform going on. What I do is I then lerp through that weight from 0 to 1. Well, actually, first thing I do is, let's say there's an NPC nearby. So if there's an NPC nearby, I then say, if you've pressed E, in this case, you know, you're nearby someone, you press E, make the transform of the that target object the same as the NPC. You know, just make it there, and then lerp from 0 to 1. So now that target is just sitting on the NPC, and then it lerps from 0 to 1. It goes, oh, I'm going to go pick that up. And then once that happens, I just do a series of kind of events of like, okay, well, let's see, I put a box collider. Oh, well, okay, if NPC overlapped with the box collider on the tip, cool, we've picked them up. And then from that point, I just kind of make the NPC a child of the tip. And then now it's just stuck there. And then so now, after I pick them up, I lerp from 1 back to 0, so it just goes back to its normal position, and then I just transform back. So, what I'll actually demonstrate, yes. Yeah, I'm almost done. Sorry, lerp is in what? No, lerp is in reference to, and from a code perspective, over time, just switching from like the code right here. I just say the weight of the tip, lerp from 0, or actually no, it would be from what it is. It starts out as, which in this case I guess would be 1, and goes to 0, and I give it a speed over time, and it just goes there or back. Yeah, I'm changing the weight, because all I'm doing is saying, okay, go to where I've set it or back. So I'll just with that information in mind, and then I'll be done. I'm just going to demonstrate that one more time. The arm's sticking out, but honestly, it's okay. Let me just hit this fella right here. We're going to bonk him. And now, well, okay, I left the robot arm out, so that's not great, but the animation's going to start anyways. Let's go here. Once again, slowly, it just extends it out, lerps to that spot, lerps it back, and then the translation happens. Now, of course, yeah, I mean, the robot arm is sticking out right now, so it's going to go back to what it was. But does that kind of make sense? Is there any confusion anywhere? Because I can clarify. Yeah. it's more the obedience of what you're doing. So like if it's halfway, like if the spot's here and like the arms, the default's like this, at halfway it's gonna like be in the middle. It's just the obedience. I honestly haven't really found a reason why you would only do like halfway, because you kind of only want either from like 0 to 1. But that's essentially what I did. Yeah.
Just like
It's for the sake of smoothness. That's what Michael mentioned, is that like, because you can slowly make it happen over time. Yeah, no, I really, this has introduced me to some really cool stuff that I'm now going to use later on. So I'm really glad that this was like a thing that I chose to do, and now I kind of know how it works, and now you guys know how it works. So yeah, thank you. I'm gonna unplug that. Yeah.
Like first, like first on the PowerPoint. All right, awesome presentation. Supposedly my voice was a little bit crunchier than Marissa's, so hopefully this works out. But dude, Andrew, are you okay? You came in like, out of breath. Oh no! Oh, there we go. Yeah. I flicked it off for a second. Do you want like a minute? Should someone else like go? Or do you want to talk about geometry nodes? Are you up for that? Okay, cool. Yeah. Here, yeah. Come up here. I'll pull up your PowerPoint. Make us like be a tiny bottom of the room thing. Get you mic'd up. You need water. If you need time, man. Like it's. Yeah, you can talk about mazes. Cool. He's getting up. We'll give it to Andrew. Michael K, everybody. We've never seen him before. He's very big on the Discord, dude. It's good to see you. That's really cool. Okay, let me pull up the slideshow on the actual Streamlabs feed, and we'll carry on in a second. So I should be able to move this here, put this here, slideshow. Okay, and then camera control, auto tracking. Andrew's the main character. I'll just give you this.
All right.
Pocket as well.
Yeah. All right, cool. Picking up or. All right, nice.
Cool.
Need to be able to look at the slides. Though.
Yeah.
Is there an easy way to switch between them, or? I guess it's we just clicking out. We're just going next.
Yeah.
All right. I wasn't sure we have like the controller, like the.
I'm sorry.
No, you're good. You're good.
I don't-
I don't think so. I think it doesn't need to be like a touching, like a. All right. Procedural modeling. So, over the past few days, I've been working on this. What's up there? Okay. Did I walk over there? Or? Okay. All right. Nice. There we go. All right. So, the bridge procedural model I've been working on using geometry nodes in Blender. Does everyone here know what geometry nodes are? Or anyone does anyone not know at all what it is? All right. So just a simple little explanation. Geometry nodes is a node system inside Blender, 3D modeling software, that allows you to kind of do a lot of different cool things. One of the things being procedural modeling. So you can enter in different values and kind of very precisely kind of select what sizing you want for different, meshes or curves. And it just gives a lot more versatility and allows you to create some really cool stuff like this. So I guess we can start here, going to the next slide. So this is the entire node system for the bridge model that I've worked on. We have 6 main parts, and up there in the top right, we can see the entire node system I worked on, which might look like a lot, but we're going to break through it. It's really not hard at all. And then at the bottom here, you can see these are all the different parameters that you can mess around with to be able to change it from the length of the bridge, floor bending, even the rope height, all that stuff. All right, so we can move on to the first part, the planks. So this is the entire, plank section, this little chunk of the node graph. And this is basically what it outputs. So this is the very first part, the A part, creating a plank using the quadrilateral, there we go, curve. And the reason also I chose a curve over a pivot mesh, we'll talk about here in a second. So, well, now let's so in the top right here, we can see we're using the wood length and wood width, and we're kind of putting it into the different values of the quad curve. And in that quad curve node, you can actually choose to just specify by a height and width value. But I instead chose to go actually moving each specific point because I wanted a bit more control over exactly where the points were, and so I could add some angle and change within the corners and how they operated. And so the reason I chose to do a curve instead of a primitive mesh is because it makes it really easy to do curving on the edges right here. Once we extrude it, there'll be easy curves we can do there using the fillet curve node. Makes it super simple. So all it does is it very put in a radius value, and it just easily just kind of bends it up. It's almost like beveling out the sides of it on the corners. That's basically all it does. All right, so we can move on to the next slide here. So all we do here is we take that kind of curve, rectangle that we just made, and we extrude it up. And you can see the fillet curve at the very left there and kind of what it does. Just you put in a radius and that curves it by whatever value you put into that rounded amount parameter. Following that, we fill the curve, so that's actually a mesh because we can't do anything with just a curve. That's not going to work. And then after that, we turn into we have to basically flip the faces here at the very right, you'll see. And the reason that is because when we extrude this out, the bottom face is gone. There's no bottom face. So all it's left with is basically like a container with an empty bottom. So what we can do is we can actually branch out the mesh, flip faces, and then join it all together. And it just turns into a nice rectangle. And I think one thing that's really cool to notice here is that you can actually branch out from the same mesh and then join it together. So it's like using using the same mesh twice without having to recreate an entire curve of the mesh, an entire whole thing just for the bottom face. And then, yeah, at the very end, we will merge by distance so that we're not left with like this loose geometry at the very bottom. And then finally, we need to take this singular plank and we can turn it into a nice curve so it's actually like a bridge. So we first start with a Bezier segment, which is basically just like a nice curve that we can use to kind of bend. And we take that curve, and then we need to set it to points. The reason we need to convert it to points is so basically it'll tell us where the instances are. So it'll create a bunch of instance points along this curve, and the amount of points it'll put along that curve is going to depend on that count value that we put right there. And then we add a little bit of randomness so that basically the rotation of each of these kind of change a little bit, so it's not just straight and too good looking. We don't want that. And then we take all these instances and we take the plank that we just did and put it into this instance on points. So the instance on points will basically generate all of them along those points, and then from there we'll rotate it because it was off by 90 degrees on the Y and 90 degrees on the Z, as we can see on the very right. And so that's the entire plank section. And we'll move on to the bottom rope section here. So this is the entire bottom rope section. It's very similar to the top rope section when I get to that. And yeah, so I guess we'll go on to the first part A here. So starting with part A, what we do is, so at the very top here in the top right, we can see, so I have a divide, separate, so in the bottom, I guess bottom left of the top right here. There we go. So the reason I do this is so that the handles, as you see where this is all getting connected to, it's getting to the start handle and end handle of the Bezier segment. What that's allowing me to do is it's just allowing me to control all the bend right in the middle. So we're splitting basically the length of this entire thing in half so we get the middle, and then we're putting it in the X and then that Bezier segment up at the top right. And then that's just being put into a simple curved mesh with a curved circle changing how thick our rope is. And then the only thing left to do is to basically turn this into a second one because we want two ropes, one on each side of the bridge. To do that, all we need to do is what we're doing here is we're taking we're using the beams here, which I haven't shown yet. we're basically taking the beams and using this so it connects to the beams correctly. And so when we move the beams, the rope moves with it. And we're taking the offsets of the beams as well as the length of the wood so it kind of scales on both the Y direction. And then we're basically just adding it all together, putting it into a curved line for the start and end points. Now we're taking that curve, putting it to a curved points, and instancing it. And just to give you an idea of what that curved line looks like, it's basically just going to be like a line, straight line like this, and it's just making two instances, one here, one here. And so then we just put the instance on each side of the rope, and that's this entire thing basically. And yeah, that's really it for the top for the bottom section. So here's the top section, very, very similar. Basically, the only difference between the bottom and the top is that I wanted to make it so that I had my own independent way of controlling the. Maybe I guess if I need it, I don't know. So what I did here is I wanted to make it independent so that the bendiness, I could change the bendiness at the top, and then the bottom was its own independent thing. So it wasn't, they had their own. That's basically what the entire bottom thing is, the blue part, and it's just connecting up to the Bezier statement. We can go to the next slide, kind of show more clearly what it's doing. So we can see we have a top rope bendiness input I'm using. And then it's just going into the Bezier segment, basically identical to the bottom rope, but just in the top area instead. And then we're doing curved mesh, curved circle, top rope thickness, the same thing basically as the bottom rope. And then lastly, same exact thing for the, okay. So yeah, same exact thing for finishing it off as the bottom rope. What we're doing is using the beam offset and putting it into the curved line, same kind of line, and transforming it to move it to how we want it to be. We did one on the Y just so it was slightly offset a little bit. And yeah, then we just instance it, and that was about it. This part is pretty simple. It's just the rope on the beams. So it's we'll get to actually the picture after in a second here. That's what it basically looks like. It's the rope that goes around the beams. And all that's I'm doing here is I'm taking the curved circle, curved mesh, two curved circles, and basically this one is the, here, we can kind of draw here, I guess. So this one is kind of the circle. So that top one right there is just a circle. And this bottom one is what gives it its thickness. So it's what makes it like actually kind of 3D pop out. That's going into the profile curve. And so then we're just putting that instance points. And I think this is really cool, something that I found that this highlights very well, and something I was talking about a little earlier, is that you can just drag out the instances and then put them into different transforms instead of having to remake an entire instance system. So basically how I did this was, like, for instance, I dragged this instance, put in what that was basically like two of the beam circles, or the beam rope circle things. And then I drag this down and I offset it by 1.7 meters. So that's going to be the ones, well, a little hard, might be hard to see. Basically, I offset it a bit. It's these two, basically just this. At the top here, I did the same thing, but I offset it by basically moving it down a little bit from the height right there. So that's going to be the top sections. And that basically just finishes off all four, or I guess all 8 of these circles, just by using this one instance on points and offsetting the transform value and joining it all together. Yeah, and that's what it looks like. Now we get on to the beam section. So this left area here, basically what we do is we set the point, set the position of each of the points of the quad curve based on offset and the wood plank length. And the left side might look a little kind of weird, or it might look like a bit like a lot, but it really isn't much. All I'm doing is I'm putting the offsets and the wood length into different multiply and add values and calculations, and then putting them into combines. Honestly, the easiest way for you to do this is just mess around with, like, get a quad and just start messing with the points, and you'll see what I'm like what it's doing. So it makes it pretty easy by just messing around with the entire notes to get a feel of what actually is happening. And so basically, the blue dots here is what the quad points are going to become. So as you can see, it's a rectangle, basically, and those are each of the 4 points. And those are going into, of course, the instance on points. That's where we want these beams to be instantiated. And it's a simple cube for the beam. And lastly, we got the ID mapping, which I thought was really cool that we could do vertex painting automatically using the capture attribute node. And we can see for the beams, I could just put orange, and I basically put this capture attribute, the color instance. And I just put whatever color I want this ID mapped vertex paint to be on this, on all the beams. I do the same for the rope. I do the same for the planks, different colors, to make it easier when I go into substance. And then lastly, after we get all of this calculated, we add all the attributes together on the next slide. We can see, so what we do is we add them up all together, just add the entire thing up, and then we put it into the group output, and we just put it, what you can do is you literally can just drag that vector, throw it into that little, and it'll create its own thing. We'll just call it attribute. Literally, it'll just give you this. It'll give you a nice vertex painted, easy, so you can just go into substance. If you want to go ID mapping, boom, right there. You don't have to do it yourself. That's pretty much it. I might have got a little quick, it might have been hard to understand, but if you have any questions, yeah. So unfortunately, there's one thing I've just been trying to figure out. I don't think it's possible, at least easily, is UV mapping in order, UV unwrapping it in order to be able to make texturing easier. The problem is that you can't smart UV unwrap in the node system currently for some reason. You have to give it a selection in seams to automatically do it. I have not really found a good way to easily give it seams to do the entire bridge. It's not bad if you're doing like a weird using noise and random procedural way of adding the seams if you want to I don't know, create some weird UV effect. But in terms of regular UV, you kind of have to do it yourself or smart UV unwrap it after the fact. I mean, there is texture painting inside Blender. I think if you just straight paint it, I don't know if you actually need UV to UV unwrap it. And if it's within Blender, I don't think you have to. But I'm not sure, how that exports out exactly, but you might have to. I don't use texture inside Blender at all. I don't do any of it. Okay, well, I mean, if you want to answer, I can. Anyone else have a question? Yeah. So at least I have it exporting. You export it as a single model. So basically, you're going to go back in Blender if you want to create a new one. It's not something at least that I know. I mean, I'm sure that if you use something I think Houdini, you probably could There's a plugin. Okay. Okay, nice. Okay, there is support. Nice. All right. Well, there we go. All right. I guess is that it? All right.
Yeah. Cool. That was awesome. Yeah, I'm just gonna make an effort to vaguely answer the texturing question because there's a few approaches that I can think of. That was an awesome PowerPoint, Andrew. Thank you. Oh, it's following you all the way to your seat. Oh man, action adventure. So one of the questions that we got was bad. It's on you. The camera was on you for a second. I'm pretty sure you're next, right, with bugs, I think, but I'll answer some of the questions we had was how do you procedurally texture things? And and Andrew responded about smart UV unwrapping, which is an algorithm that Blender supports where it automatically tries to place seams at points of high concavity. And then, so if it's a really complex edge, it'll just mark a seam there and cut the mesh from there. Blender, I don't think, has nodes that support that yet, but it continues to upgrade them. Houdini definitely does. And then Houdini has a lot of other automatic tools for UVing. So there's automatic UV packing. It has an incredibly fast algorithm for optimal UV packing, which is trying to squeeze all the UVs into the 2D space and try to make them as big as possible while fitting them into that 2D box. When it comes to actually procedurally texturing anything, you need to start with like noise, and then apply like things to it. So there's a program for that called Substance Designer, but you can't really do it natively in Blender, except you can because there's this one group of like nerds that made a fork of Blender that is attempting to be a copy of Substance Designer, and it's there is like I think it's called Armor Paint, and you can do procedural texturing in Blender. You can use the shader editor. So Blender has an entire node system for the shader editor that does more than just shaders. It does do some like texture manipulations as well. And you can go in there and you can crank out procedural textures in there. And then like if Blender one day adds a node that's like a baking step, you would be able to probably bake that out onto a mesh and export it. But that's typically not your goal with these things if you're doing them for game development. For game development, you want the textures to be controlled from the engine. You don't want them to be controlled in some external software because you want your artists to be able to iterate really quickly in engine. So that's where the geometry nodes plugin for Unreal Engine comes in, or the Houdini engine plugin for Houdini, which is supported everywhere. But yeah, I hope that answers that question. Yeah. All right. So bugs, right? Yeah. Let me switch the PowerPoint up. Yeah, lots of bugs in design. How to quickly bring a prototype to life. Oh my God, what a GDC title. No, I like it. I think one person's gonna have a mic. Yeah, sorry about that. Oh my, you got notes? All right, here we go.
I mean, we can alternate. Not used one of these before. Testing. 1, 2, 3. Is it working fine?
Yeah.
All right. All right. Brody, you want to? Okay, cool. All right. Hi, I'm JJ. This is Brody. We worked on the DevLUp Game Jam 2022 this year on bugs. And so we'll be talking about how we sort of brought this idea, came up with this idea, and like figured out a good way to execute it. In order to come up with the idea, one easy way to come up with an idea is to take an assumption that games make and subvert it. And so a core assumption in a lot of games is that there's a unique player character with unique characteristics, like unique to the player, and that all of the enemies and environment are designed around responding to the player's actions. So like Mario, like Goombas are meant to be stomped on. There's all kinds of things in that game that are for the player. But we decided to subvert it and make it so that everything, all of the elements in the game are equal. They're the same. It's symmetrical instead of asymmetrical. And so that is an idea that has potential, but how do you execute that idea in 48 hours? So in order to do this, you need to, it's important to plan. So we took inspiration from 2 different sources. We had Brody, the first thing that came to Brody's mind was Wii Tanks, which was for the Wii. It's like a arena shooter where you take control of a tank and you try and kill all the other tanks in the game. And there's many different, because of the level design, there's many different approaches. You can take advantage of the environment to sort of achieve the same goal in different ways. And generally, all the tanks have similar abilities to you, which helped with the symmetry idea. And then for Into the Breach, a lot of the units, all of the units act by the same rules. So damage and push, for example, can unintentionally cause collateral and like harm your buildings or harm your units, or you can use it to your advantage as, say, the bugs harm each other. And so in both of these scenarios, a lot of the complexity of the gameplay was created by the rules, not necessarily by the AI. There's ways to design your game to take advantage of an idea and like bring it to like an emergent level of complexity. So once you have an idea, start making stuff, and really important thing is to scope. In my case, I find it easy to prototype with 2D assets, and it's also easy for the programmer to work with to quickly put those assets in the game, implement them, and there's a good balance between planning and testing, like play testing. If you plan too much, you can end up with a lot of ideas on paper that sound cool, but when you actually start trying to program them in, they might end up more complicated than what you envisioned, or they're just not fun. Alternatively, if you go straight into testing without planning, without having come up with a strong core conceit, you might end up having work that you would have to like scrap, or end up with systems that are unwieldy, ideas that are unwieldy and need to be reworked, which is not great when you only have 48 hours. So striking the balance between these two is definitely important. And I will pass it to Brody to explain how he implemented it.
Testing. Is that okay? All right. So I'm here to talk more specifically about the AI, since I was programming side. And just by the way, the game is called Bugs, which stands for Bots Under Great Strife. They're bug bots, and there's also AI. A lot of puns. Next slide. So just a little overview. I'm first going to go over the architecture of the code and talk about, specifically for a game jam, being able to quickly iterate and kind of hack a lot of shit. Sorry for my language. Get my notes. And then I'm going to go over specifically how we implemented the AI from a design standpoint, and how it created, even though it was very simple, we got some complex outcomes through like emergent behavior. So brains. One of the first things that we decided was that the bugs were going to be pretty much identical, whether or not they're being controlled by a player or by an AI. And the theme of the jam, if you're not aware, was just pick one. So the game starts, and the player then sees the entire level, you could say, and then chooses which bug they will play as for the level. So regardless of how the level starts, everything should work fine, regardless of like who the player chooses. So the way we programmed this was we had the bugs themselves, I divided it into what I called a body and a brain script. I don't know if there's more industry standard terms for this kind of design pattern, but the body script would control movement and shooting and how those actually functioned for each individual bug. And then it would accept a separate script for the brain that would have very limited coupling. And that way we could easily develop new brains, we could swap them out, and quickly iterate on the AI. Next slide now. So one thing with developing the code is that awful stuff can be okay at first. Iterability is key, and I think there's, as programmers, we often talk about performance and making things fast. And while that's true, we want things to run fast, we also want code that reads fast and we can write it fast. So an example here is just some silly comment. This is horrible code. It does not work. If we were to continue to use this, it would lag up everything. I would have code that would run every frame doing erroneous checks. Horrible code, but I wrote it in 5 minutes, and now we have something that we can check, we can test, we can iterate on, and we can move forward. With that being said, I don't know if I have this in this slide or the next slide. Prototyping is very good, but please go back and refactor your code. And then a benefit of doing all this is that if you plan this stuff out, you get to spend the last 6 hours of your jam actually working on your game and not just trying to like fix all the bugs you've accrued. I think next slide now. Right. I skipped a slide somewhere in there. But going on to the bugs themselves, they're very simple, extremely stupid. This is one, literally 3 lines of code. In general, they just follow 2 main things: choose a direction to move in, and then shoot. So some of those are controlled on a timer. Like some of the scripts, after a timer goes off, it'll choose a random direction to move in, and then say whenever it's close, or it's always trying to attack the player, but it will only succeed when it's close. Slide now. Despite this, the game kind of works. I mean, everything's really simple, but we get some, it doesn't look like a bunch of bugs are just hoarding up and doing the exact same thing. And how did we do this? So I think it's kind of 3 main things. So first of all, the previous design work that JJ talked about, that really paid off. Like at one point we had built up on the whiteboard like this huge sort of skill diagram of different things that bugs could be good at. So like damage or speed or maneuvering around the environment. And we separated, once we had that diagram built, we could say, oh, this bug is really good in this area, so we need something on the opposite end that could counter it. When you draw that out, you get to quickly see different niches that different bugs can fill. I love saying bugs all the time. And so, for example, like the laser bug up top is something that's generally on the outskirts and won't, there's like a very far away thing. Meanwhile, like the charging one is always kind of more of an immediate threat. And to help enforce that, we had, we divided the bugs into thirds. So 1/3 would always be moving away from the player, 1/3 would be moving towards, and then the other was random. So rather than a bunch of bugs just immediately like rushing towards wherever the player was, they all kind of spread themselves out, and it felt more like they had agency. And to complement this, we also allowed them to damage each other. And this was a really easy thing to make it feel more like a free-for-all. Even though everything was targeting and everything was built for the player, it felt kind of as if it was this huge hectic battle royale. And then the last thing is something I kind of touched on, but varying levels of priority. So for example, as soon as this GIF starts, the charging bug goes straight towards the center. And I think the charge is an instant kill, and it's a pretty big threat. Meanwhile, the laser up top, he kind of tucks himself away into a corner. And so just by creating that corner up there where it has walls that it can't shoot past, we've now set up this system where the player has different levels of priority of what they need to take care of when they start the level. And that can easily change through how we set up the environment and through every level. Even though they're the exact same bugs, the bugs don't know what they're doing. We just use level design to create more interesting gameplay events. I think that's the next slide. In conclusion, as JJ mentioned, there's a big balance between planning ahead of time and also iterating. You know, you need to do things fast, but you also need to do things smart. And then second point is do not underestimate the power of simplicity when given room to grow. You can get some really cool, emergent, interactive stuff. I think next slide, finished. Any questions? Right? Yes, it was Godot, yeah. So that was simply because it was something I had the most experience in. I think JJ uses Game Maker Studio too, but he was going to focus on art and sound and design and more art and literally everything. This guy is crazy. He produced so much content. And even though I wanted to do something 3D for this jam, we decided that 2D was something we were both more comfortable with. And Godot, not only am I more comfortable with, but it's really great at kind of outputting those low performance but quick to make prototypes. Right, yeah. Any other questions? All right, thank you.
Oh, yeah.
No. All right. Yeah, no, nice. Very nice. That's pretty good. Thank you. Okay, yeah, and I think now it's like Michael's presentation on oh. Yep, there we go. Oh man. Here. This is a really cool way to meet.
Check. Yeah, I think that we're good. Okay. Hey guys, I'm a PhD student here. I just posted some other ways of like seeing some of these sorts of random things. I put up a suggestion on the DevLUp UF group. If you want to do a Code Wars clan, go ahead, vote for it or whatever. Anyway, next slide. So I'm going to talk about mazes, but not actually this kind of maze. Next slide. Yeah. So those things are linked. So just don't click on the image. There we go. So there are various things that I did not create, like the picture of the colon. This grid image, a pathway through a graph. And so you can think of mazes in a large number of ways. And generally, people think of them as graphs dealing with spatial connectivity. And if you look at the yellow here as it reveals itself, but you saw it. So yeah, that's fine. There we go. So basically, it's picking an edge and going to a space, and if it's visited, it removes the wall. And effectively, this could be spatial. It could be logical, conceptual. So you could make mazes that are actually really complicated verbal riddles or something crazy. So the definition is pretty vague. But yeah, mostly it's this sort of stuff where you either visualize the paths, which is the yellow, or the walls, which are the blue. So go back. Next slide. And there was one note there that normally they're trees, which means that there's no cycles within the graph. So if you're doing a maze, you got to ask yourself, why are you doing it? Sometimes things are thrown into projects that aren't really connected to the core mission. And one thing that's really problematic is just having large, meaningless spaces. So try to avoid that when you're designing any sort. And one of the things that you might want to consider is, can you do something kind of creative with the maze structure? Like, is there some neat twist? Is the player creating the maze? Can you not see the walls or something like that? So there are some ideas there. Next slide. So I figured, okay, our group wants a maze. How do I do this? I went to Wikipedia, found an algorithm, and just started coding away in Unity with C#. And it took a bit, I don't know, like 5 hours because I was unfamiliar with Unity and some of the C# that I needed. But it wasn't that bad. Now this is a Pygame implementation just to show the logic of the algorithm. So the algorithm I picked is the Aldous-Broder algorithm. And there's one huge problem with it, which is it's not guaranteed to finish. And so the step goes, you pick a cell randomly, and then you go to one of its 4 neighbors. If that cell has been visited before, you still go to that and mark it as the current neighbor. But if not, you remove the wall between the cell you were just at and the next grid point. And you just keep going until you've explored the full grid. You don't have to explore the full grid. You could leave empty space. You could designate, hey, I'm only going to explore for this number of steps. So that's one way that you can get past the constraint or flaw of this algorithm, which is there's potentially an infinite number of steps to complete even a 2x2 grid. It could just oscillate back and forth between the two grid coordinates. Granted, that becomes like exponentially unlikely as you do that, but it's something to consider. So I did it in Unity and C#, but I figured, oh wait, Godot has C# too. How hard would it be to switch over the code from Unity to Godot? And I want to say it took me about an hour to do that. Granted, I didn't set up as fancy rendering and stuff. Then I tried again. I'm like, all right, Godot with C# to Godot script. Pretty easy, pretty much the same stuff. Granted, the data types needed to change a little bit. But Godot script's a lot like Python. So I was like, well, what about Python and Pygame? And then, you know, I changed it up quite a bit because I just code Python better. So I wanted to like make a better structure for it. Well, I also wanted to visualize it step by step and do some other fancy stuff. So it's the same thing. It was a backup. So next slide. Interesting. There's like 2 there or something. If you have the data for the connectivity of the graph, it still has to be visualized. And the question is, how are you going to visualize it? Now, you could just connect rounds like this, but that's not terribly exciting, and it's not very game-like. So the next thing you might want to consider is, okay, what's your art budget look like? What do you have for artists on your team? What art assets can you find that are free to use? And so one point, so the top one is actually from a game jam that we did, I don't know, 6 months ago or something. I forget who was even on the team. But yeah, we just found these art assets. We threw them together and we like stretched it and stuff. And it looked fine to me. You can explore, you run into walls, whatever. Now, the top one is visualizing the walls. That was the blue from the prior graph a couple slides ago. The bottom one over here is visualizing the path, which is the yellow. Now, you can see it's basic. It's the very different visualization for effectively the same data. And that I thought was a pretty interesting little find. Now, you can see that there's quite a I was tiling with squares, but you can tile with triangles or hexagons. So the hexagon is just 6 equilateral triangles. Now, and you could do skew shapes and stuff like that too. Now you see, you don't even need the same shape. You could have gaps. You see the green gaps here, or red could be doors that are connected. Big 12-sided. So, oh right, yeah, it would be 12. So you could have, little arena rooms that are connected as a maze, but through some level. Who knows? Anyway, you've got ways to visualize, but you don't want to have the person implementing the maze finish before the next person starts, because then you'll run out of time during game jam. So you kind of want to come up with strategies for any task on how to break it up so that each person can work in unison on the same sorts of things. So if I were to do this sort of thing again, I would say, all right, so someone's coming up with the maze generation. They're figuring out how all of the grid coordinates or whatever are connected. Boilerplate data type should be defined. And then at that point, the coder can say, all right, I'm going to go work on how to implement the maze and connectivity. And then another coder could say, all right, I'm going to work with the artist on how to populate the maze with a dummy graph that could be handmade, could be just like randomly generated with like on and off, whatever, just to give a sample for how the end product will look when the first person who's doing the actual generation side will be finished. So at that point, artists can start cranking out assets. You've got walls and floor tiles, ceiling tiles. You could have ladders or skeletons, little monsters to interact with inside the maze. Now, it's not a bunch of blank rooms that you're connecting your players to, in the last, 2 hours of the jam. So another benefit of having these sorts of structures is that you've got a way to do the pathing already. You can say, all right, well, where is the monster right now? Well, where's the player? All right, I'm going to do a depth first search or something. But you could do much simpler things, as before our previous presenter pointed out. We just move in a direction. I thought that was brilliant. Very effective use of a simple rule to give a very powerful mode of interaction and behavior. And a lot of emergent behavior is simple rules that are combined together in interesting ways, and you get some really powerful unexpected results. So another thing here is random walk. You could have the enemies just randomly walk around. If they see the player, they attack. If not, they just kind of stumble along. So you can see dungeon map, really classic. Basically, it's a maze, and it's just the art team did a really good job at making it all tie together, style and yeah. This is one person's work. It's linked if you decide to click on it later. Excellent. Great. Yeah, so I was curious how bad the performance really was, because I noticed when I tried to do like 100 by 100, it just froze on me. I'm like, well, that's not good. I might want to make a bunch of mazes. But honestly, the generation isn't really that important, because you're probably going to generate it once every now and then. The more important thing to be efficient is stuff like the pathing. So if you're doing a tower defense game and the player is placing blockages like towers or something like that, then the enemies are going to have to update their pathfinding whenever the player modifies the underlying data that generates the maze. So I did step-by-step iterations through the maze, counted the number of steps for a bunch of different things, did it in parallel, so the timing was a little bit wonky. But generally, you see the curve is effectively the number, the size of the grid. It was S by S, so that cubed. And you can get by with that. You've got 0.2 seconds at a 40 by 40 grid. I don't know about you, but I don't really want to climb through 1,600 different grid coordinates to get to the next level. But nor you could think, okay, I want to find a way to do some of these things more efficiently or inefficiently. There are assets that are really heavy, lots of polygons for the wall shapes or something like that. Then you might have to simplify it, or just the collisions. You could do it in 2D too. So if you're doing 2D, you could use tile sets, and the walls then potentially become empty tiles. And the removed walls would just be an extra floor tile. Then from there, you can do the corresponding auto tiling based off of what the neighboring tiles are. Yeah, I think that's it. Guys? Go for it. So I did it kind of a ridiculous, silly way that didn't make a lot of sense. I had horizontal walls and vertical walls as separate grids. And when I moved from one position to another, I just did a lookup in that corresponding thing and then did that. You could have a 2D matrix where each tile has top down, left, right walls. And then when it removes, let's say, a bottom wall, it also would go to the corresponding bottom and remove the top wall or something like that. So there are lots of ways that you can implement these things, and yeah. So think about graph theory and how general it is. You could have the mazes potentially be like circuit board type stuff, or like arbitrage type financial trading pathways. So now it would be a very strange thing in that sense, but in a kind of common example that you've probably seen before is a choose your own adventure story. So that is a path to a particular ending. Now, could you say that that's a collection of paths? Yeah, that satisfies that particular definition of a maze. It's all effectively dialogue at that point and a few choices. I would say that's probably the most exotic, weird thing that I've come up with, but maybe mathematics can also be considered mazes, where you're trying to get from a starting place of axioms all the way to a particular proof or the end statement of your provable topic. So now if you can actually like quantify that or qualify that connectivity, you can maybe even do graph search on the space of mathematics. And then at that point, basically anything could potentially be. Good.
Yeah. Oh, it's really nice meeting you. Like that was awesome. That was really good. Okay, yeah. Oh, and it's doing the main character thing. You're still on. Right, yeah. All right, yeah. So we are at time. I mean that was a solid hour. And that's honestly, I couldn't have asked for better presentations. I can still. I was planning on filling in with like some of the VFX I did for Campbell Combat, but like only if we didn't have enough time. Otherwise, it would feel almost like some sort of nepotism or something if I just gave myself like the opportunity to present. So yeah, I think that's it for today. I appreciate. You know what? It was like there were some clever techniques that I was trying based on. Yeah, so I'm glad. If you'd like, I'm prepared to give a talk on that right now. But if people want to head out, that's also understandable. There's a football game, so honestly, like, yeah. Do you guys want to hear about it? Alex gives me the thumbs up. Andrew gives me the thumbs up. Brody's heading out. Understandable. Yeah, feel free to head out, guys. Yeah. In fact, it's a live stream, so it's being recorded actively. And hopefully at a better quality than than is necessary to like require photo editing. So yeah. Bye, Andrew. Okay. Yeah, I'll pull it up. Why not? We'll do a little bit about the CFD stuff. Let me just parsec into my home computer real quick, and we'll move on from there. Huh. Heading out. Let me give me a second, guys. I think this is worth sharing because it's some interesting stuff. There were some very unique like effects that hadn't been implemented before. So 7 and 2AB, nice. Not me actually saying my password out loud into the microphone as we're recording, as I type it. That's probably not a great idea. Okay, let's try again. Yeah, ever since we got hacked, security's been, oh my. Oh, I'm trying to log into the DevLUp, right. All right, 1 second, guys. See that? Two. Yes. Oh my. Struggling here. Sorry. That's got to be it. There we go. Oh. And then Authy, of course. But yeah, so I'm going to talk a little bit about the candle head, just because why not? While we have a little bit of time here, as well as oh man, here we go. So yeah, the candle head, as well as the candle fluid physics that I was messing around with in the process of making our little candle guy, who unfortunately we were doing from a very zoomed out perspective, but like, you know, John Wick, he needed a face, and so yeah, here we go. There we go. All right. Yes, there we go. I'll pull up Unity and all right, any minute now. I can close this down. Be small. Open up the project. Oh yeah, not compile 8,000 shaders. Yeah. I'm glad the stream is going pretty decently, and there's not that much crunchiness. That's really good. That's a really good indicator. The project has changed quite a bit, so you guys are going to be seeing this project with Gator Club in about a week from now. A week to 2 weeks from now, we're going to be doing a workshop on AI in video games, and that's really exciting. Alex has worked towards that. William's doing a lot of the work. William is doing 99% of the work. Yeah, and then Kyle is from Gator Club will be coming in to do some stuff there as well. It's from Star Citizen's concept art. Yeah. I just have a bunch of desktop backgrounds that I swap out from the ones that I like. Where's John Wick? Let me see if I can navigate the scene here and find a nice spot to show off John himself. Let's see if we can find another test scene, though I'm not sure that we have. I could make a new scene. I don't. Yeah, here I'll just grab the candle head. So the John Wick head is one of the cooler things I think that I've had to put together. If I just make this full screen, drag this out to the side. So this is a little visual effect for John Wick's head. There he is. So this was originally going to be John Wick's flame head right here. We were. Can I grab him? Will I get lucky? There you go. He was going to be very like capable of moving around. So kind of like that. But with the issues that we were running into is that because we were spawning a bunch of particles that were running on shaders, it was leaving like this really long trail from all these like stretched out particles. It was not very good. So this was the first iteration, and the way that this worked was primarily using particle strips, but they just it wasn't very clean. I don't remember what the fundamental difference I made was. I think this is before I really heavily iterated on it. Then we switched to the new John Wick, just way more stable and in 3D. You can barely see it on these monitors, unfortunately, but he has eyes. He has eyes, and they can emote. So let's show that off a little bit. He has. Let's see. We can. You can change the noisiness of the fire, kind of make him be like really angry. John Wick raging. But more importantly, the eye color, I can just turn off the color, make it a little bit darker for the fire. It's these values right here that are killing us here with their brightness. You can see the eyes here now a lot more clearly. Not too clearly though, because they're still really bright. Yeah, they're pretty long. And so we had some controls for like eye spacing. You could be like, oh, I don't understand. We had like, you could wink, you know. He could squint both of his eyes. And then if we turn off eye squint, we can like, you can lower one of the eyebrows, or you can lower both of the eyebrows, be like angry. So just a little bit of fun there that I thought was worth showing off. It'll be very angry. Yeah, if we just really crank up the fire noise speed, he gets very. But most importantly, when you move him around, he doesn't respond to velocity, and he actually takes in a velocity input in real time from the character to move him around. So this is the like underlying VFX graph. This is my first time working with particle systems in a VFX graph ever, and also my first time in Unity specifically. I hadn't really done stuff with Niagara before in Unreal Engine, so it was really fun learning all of this. There's a lot of curves here that are being used to drive the different effects, to drive things like transparency over time for each individual particle, so that you can say, you know, low transparency here, high transparency here, low transparency there, and you get like these different patches of eye that you can show. And by shifting that curve up and down, you can isolate parts of the eye that you want to make visible or render. And yeah, I mean, that's fundamentally like what's going on here, right? Like we're taking in qualities over here, like I mean, there's a lot of attributes that were being used and set early on to then reference later on. So like set percent over here is like a per particle system attribute, even though they're all part of the same VFX graph. You need to know like for the eye, which is its own particle strip, there's three strips going on. There's the head, and then there's the eye and the eye. And all of those have like an index of what number particle each particle is within its own strip. So you set that as like a percentage value that you can then reference in the shader for each of these each of these strips to drive the different effects. So like at 5% you are this bright, at 30% you are that bright, at 10% you are that bright. The reason you have to do that is because normally you wouldn't be able to access a per particle attribute when it's a particle system with three different ribbons, because it would treat them all as like part of the same indices. So this code here separates that out and lets you actually access like the index of the particle within its own strip. So each eye goes from like 1 to 20. Each, the head goes from 1 to 20. And like that's it. It's all just a bunch of curves here that are drawing all these different effects, moving things around. Custom Bezier curve that gets noised up and moved around using curl noise. And that Bezier curve is like the curve that the candle follows. And based on the velocity of the character's input, different like parts of that curve are weighted differently in the negative direction of the velocity. So players moving to the right, the curve goes like, all right, let me move this point a little bit, this point a lot, and this point really far. And so the candle like kind of does this when you run around. And that's it. That's all it really is. This isn't. It's not that much, but like this took me like 2 hours to make, maybe 2-3 hours. This isn't. I mean, and it was a lot of like exploring stuff because first time. The more exciting stuff was the candle splashes. I really wanted to create this like splash effect when wax, like when a candle got shot, I wanted it to splash off of it. So the way we did that is I'm not sure, things have been a little reorganized here with wax splatter. Here we go. So this is the wax splatter graph, and this is a pretty simple graph, but it's some of the other efforts that went into it that really worked on it. So if I add a light to the scene, how do we add like a simple primitive light in Unity? Is that a thing? Right click the hierarchy. Light, directional light, nice. And then I can probably crank up the intensity globally. Oh. I see. Is the angle, the angle by default is at a, I see. There we go. We have the ambient lighting in the scene turned down pretty heavily, don't we? There we go, that's a little better. That's from our perspective. So what this effect here does is it's the splash for when your candle gets shot, or any candle in the scene for that matter. Come on. Okay, I don't know if that's even, is that our guy? Who knows? Wax splatter. Let's just drag out another one. Yeah. All right. So, and I think if down here normally there's a little button on the bottom right. I'm not seeing it, but I know that I can trigger it from in here. So I'll just do that and do send. And so this effect looks terrible, right? Like it's not that great. But the idea was that you get this like directional splatter of wax particles that are going to come out of the candle whenever it gets shot. It's like, I wish I could show in slow motion, but the idea was to emulate an effect from Crysis 3 where there's like this massive blood splatter when an alien explodes. And so I wanted to generate a sprite sheet, and I wanted to do all this fancy stuff in Blender to generate the like most optimally packed sprite sheet I could possibly generate. And so like, oh boy. Yeah, you can see some of the later testing that I would end up doing with like the same effect. But I went in Blender and I used fluid particles. I went through so many iterations here. I tried to do computational fluid dynamics that like work within a bounded box, and then there's actual like vectors that are simulated for every point in the box over time of the fluid simulation. This, on the other hand, is fluid particles, where each particle has a radius of influence, and it affects the people that are the other particles within that radius with certain qualities like viscosity. There's like viscoelastic springs that obey Hooke's law or some other law, and like it's all. I mean, I don't fully understand everything, but I'm talking about the sort of settings that you interact with like viscosity and area of influence, and what density the particles are most comfortable at, so they attract their neighbors until their neighbors are too close, at which point they repel their neighbors. And I was really trying to create that effect. And so I took something like this in Blender and I rendered it out. And then I attempted to write a Python script that would pack all of the data vertically into like a single channel of an image. Because what I wanted, I had height data for every single frame. So every single frame had like 255 values for every pixel, right? then those 255 values were 0 to 1. It was like, it was either really far away or really close to the camera for every point in the splatter. So I know over here we're seeing like a very two-dimensional splatter, but originally the splatter was very much three-dimensional. In fact, if we go to the DevLUp website, we might be able to see, I don't know if it's still, now it's been replaced. Other people have made really cool things. It was down here for a while, the show-off post, but you'll probably even find it somewhere else. But so there was a lot of oh man, I'll find it from Michael as image. As or in show off. Oh boy. In, and so scroll through, yeah, that's all right. A few pages of content. All right. We're almost there. There we go. Yeah, so right around here. This was the original effect. And I wrote up about it a little bit. This is the effect that I generated. So you can see there's depth information there. Sometimes it's closer to the camera, sometimes it's farther away. So I rendered out the 25 different sprites of a 25-frame animation. What I wanted to do is I wanted to take this 0 to 255 value. Those are metaballs, yeah. So the way that I did this is like, it is a fluid particle simulation, which is much more efficient than a domain that has like all the vectors. However, I needed a way to like render it out like water. So how many of you have played Portal 2? Or like, okay, if you've seen the gel in Portal 2, the like orange gel and the blue gel, that's rendered with a metaball simulation. And what that is it's just like these spheres that like when they're close enough to each other, they do cube marching, which is like this algorithm that kind of just maps a surface around a volume. So each metaball defines like a sphere around it of values from 0 to 1, where like it's 1 in the center and 0 at the outside. And you define a certain like threshold for the place where you're gonna like divide the values. So you're like, okay, I'm gonna divide the values at 0.7. And so it attempts to, at the like 0.7 point, create a shell around that like field. And so if you have two metaballs next to each other, their values kind of overlap and they act like water droplets. You see them do like a little surface tension thing. And yeah, so that's what that's rendered with. Those are all a bunch of spherical metaballs. And you can see it doesn't look anywhere near as good as like my most recent iteration with Blender, which is like, actually, this is not even using metaballs, I don't believe. It's just halos. It's like these little rendered halo spots. But I realized that, yeah, it's almost, yeah, this one is almost, yeah, so this is just the particles, but not, yeah, there's no like mesh. There's no mesh there to be rendered. It's just every particle is a little circle. Yeah, thank you. So the idea was that I would render this out and it would probably create a better effect. But I have depth information. Well, depth information defines like, 0 to 1. I wanted to pack that depth information. So there's this group that worked on Sea of Thieves. And in Sea of Thieves, they have this effect where when you vomit in Sea of Thieves, there's this like animation of the vomit spreading out. And it spreads out on your screen as well. And what they did is they packed like 1 million height values that describe the different frames of the animation as a stack of 0 to 1 values in a 255 range. So like the first frame of the animation would have been like the vomit just touching the surface. And the second frame would have been like the little bit spread out splatter. And the third frame would have been like, like absolutely just splattering out. But really there would be a lot more interpolation than that. It would be like 255 frames of interpolation. And what they did is they then went into a shader and they like went down the alpha values to create this like final effect. So at the end of the day, the most spread out frame would have a value of like 1, followed by 2, followed by 3, as it would get like tighter to the center. And that's how they would isolate the different like layers in the animation. I realized that I can't do exactly that with this effect. And the reason why is because vomit spreads out it always spreads out, like it always covers new areas. So you can't stack these into a single like image if there's holes in it, because if there's holes in the vomit, like right there, then in the next frame, that hole might like move, it might expand or something. And now if you try to add these different layers of the animation together, you're going to end up with values that are inaccurate, because like it's going to be 1 plus 2 plus 3, and it's going to end up with, I mean, really, this is a, so all the different frames of the animation have a value of 1, and then you add them on top of each other. So if there's holes, you're going to have like the layer above it is going to fall into the layer below it. And you can't like write a shader that works for it anymore. I didn't even realize that. I had no idea. So I was sitting there writing like a Python script at like 2 a.m. trying to hack all this together. Learned a lot of lessons, and ended up just rendering it out as a sprite sheet instead, and doing the standard thing where you go down the frames of the animation in a single image, and got that end result. But wasn't the best. But yeah, so that's it. That's my little like tech talk. But yeah. Cool learnings. Yeah, I guess now we're like really officially done. I don't know, unless if you want to talk about Candle Con. I mean, we're all like on the way of leaving. Yeah, Michael, what's up? Yeah, I think it technically qualifies as Boids, but it's Boids with like very like the rules, because Boids are just defined rules on the particles, right? Like attract towards things or like separate or something. This is like Boids with way more like rules, just a lot of rules that come together, I think. So like that's my understanding of Blender's implementation. But at the end of the day, it's just a bunch of settings in Blender. Like it's a bunch of pretty accessible settings over here, like fluid solvers, stiffness, viscosity, buoyancy, and they're all like, these rules come together to define some big equation about what was your velocity last frame, what's your velocity now, what is your neighbor's velocity, and what will your velocity be. Yeah, that's my understanding of the underlying implementation. Yeah. I think we're done.